what we're doing is we're developing technology to detect earthquakes, well, not earthquakes, Venus quakes, from balloons. And the reason we're doing that is because the surface of Venus is extremely hot and high pressure. And so the longest anything has survived on the surface is about 127 minutes. And that, as you might imagine, is a pretty short time to be able to detect any kind of seismic activity because it's sporadic. But as it turns out, if you're about 50 kilometers, which is about, say, 5 times the altitude of a jetliner, above the surface of Venus, the temperature is actually very similar to a cold day on Earth. Like, so it's essentially, 0 Celsius or 32 Fahrenheit, roughly that level. So your sensors can actually last for much longer. And so what we're interested in doing is studying seismic activity on Venus, but given that we can't do it from the surface, we want to do it from a balloon at a vantage point where the sensor can last much longer. And so what we're doing is we're trying to do experiments on Earth to see if this is possible. And so the Ridgecrest sequence was part of these experiments because it provided us like a ready source for earthquakes, because there were a lot of aftershocks going on. And so it was like it was an event ongoing in our backyard, and like it was easy to use those events as a proof mechanism for our experiment.
So the fact that there were so many aftershocks, that just kind of allowed you guys more opportunities to study how earthquakes work and then apply it to what you're hoping to see on Venus?
Yes, exactly. So as you might imagine, earthquakes are pretty sporadic and unpredictable, right? Like, so it's hard to randomly go out and catch an earthquake. But the interesting thing with Ridgecrest was that, I mean, it's actually still like the aftershocks are still ongoing from that sequence. It's like, almost 2 years later. But in the 6 weeks following the Ridgecrest event in that Owens Valley area, it was basically ringing hundreds of times every day. And so we were pretty certain that something would happen while the balloon was in flight over that area. So it was a virtual guarantee that some quake would happen while we were in flight, which is not something you can say for other areas in the world. But at that time in that location, there were so many quakes that we felt pretty sure that something would happen while we were in flight.
So what does the balloon do?
So the balloon is actually carrying. So the balloon we used on these flights it's called a heliotrope balloon, and that's not meant for Venus application. Actually, that's purely for Earth application, and it's a balloon with darkened plastic as the skin, and it's essentially a hot air balloon because when the sun hits that dark plastic, it heats up the air inside, and so that basically makes it a hot air balloon, and it's able to lift things. And so what we did was we attached a barometer, so a air pressure sensor to it, which is very precise air pressure sensor. So not your standard variety, but like an expensive, precise one. And we floated it on the balloon. So what the balloon is doing is just carrying the barometer to an altitude, and then the barometer does the detection. So what we're trying to detect is not actually the ground moving, but when the ground moves, it also shakes the air above it ever so slightly. And we're actually trying to detect the air shaking from the ground shaking. So we're not directly measuring ground motion, we're just measuring the footprint of that ground motion in the atmosphere using this pressure sensor.
And how are you applying what the information you get from that? How are you applying it to what you're trying to do with Venus?
So for us, this was a huge technology demonstration because as it turns out on Venus, this imprinting process, so when the ground shakes and it shakes the air above it, that imprinting process is about 60 times more efficient on Venus than it is on the Earth. So for a Venus quake that is the same magnitude and the same depth and the same faulting mechanism as that on the Earth, the signal produced would be 60 times stronger. And so what we're trying to show with this experiment is that you can actually pick up quakes without being on the ground. Like it is actually perceptible from the air. And so if we can show that on Earth, because the signal is so much stronger on Venus, we expect that if there are quakes and volcanic eruptions on Venus, which is being hypothesized currently, we are able to also pick it up on Venus. And the other thing this is allowing us to do is, as you might imagine, in California we have a lot of seismometers on the ground, so we kind of always have an idea of what's actually going on the ground. But you can imagine on Venus we don't have that. Like, we don't have any seismometers on the surface that will tell us, oh, a quake has happened. So another part of our effort is to collect as many earthquake signals as possible on balloons, so that we can start studying what an earthquake signal looks like on a balloon compared to all the other noise that appears in this signal. And so this is also part of that effort, and it's a very important piece of that effort.
Yeah, interesting. What would what were you saying? So being able to detect the earthquake sound by balloons, what applications would that have on Venus or here on Earth?
So for Venus, the use case is ideal because, as I said, like, studying the internal structure of Venus is very important to understanding how it evolved, which is a big science question in the planetary science community. So for instance, on Earth, we know the Earth has like a crust, a mantle, and a core, like something, we're taught in like school. And we know all this because, we've studied through these seismometers on the surface, we've studied how seismic waves pass through the Earth's structure. And so this is an important thing to do for Venus. But the problem is, as I mentioned before, that the surface is so hot, lead melting hot, and so dense that nothing survives on the surface. And so the primary application on Venus would be for the balloon to fly around and pick up these signals generated by seismic activity. So it gives you a sense of how active Venus is as a planet in terms, how many quakes are happening at what magnitude, every year, or like whether volcanic eruptions are going on. That itself is a big result. But we've also found in this study that if you look at the signal detected by the balloon, you can also start studying the crust a little bit. So like you can say, oh, there is, this much of the crust is of this type, and then there's layering in the crust. So that's the primary application to Venus. On Earth, what we're envisioning is the application is primarily for areas where you don't have a lot of ground coverage. So like oceans, etc., where like you want to study geophysical signals, but you don't have space, or it's hard to put a ground station there and maintain it. A balloon can easily cover that area, and several companies have also performed flights with balloons that can maneuver in the air and station keep. And so these, you can also have networks of balloons that can configure themselves quickly. And so it provides a sort of mobile airborne vantage point for like a lot of signals that a ground station probably wouldn't be able to capture. So say a volcano was erupting, you can measure it from the ground, but a balloon can allow you to see what the volcano is doing acoustically, like from the air. And so those are some of the applications that you can have on Earth.
Interesting. And the acoustics that the balloons pick up. So let's go to this volcano thing you're just saying. So the acoustics that the balloon pick up from the volcano, what would that tell you about what's happening with the volcano?
Yeah, so one area that's of interest on Earth in terms of volcano acoustics is, and this happens a lot with ground-based recordings, is like people are trying to study, for instance, if they can predict a volcanic eruption about to happen by measuring the tremors just before like a major eruption happens, for instance, right? There are people who've done these studies from stations that they've placed on the ground near the volcano. But you can imagine that, that only gives you a little bit of the picture because you're on the ground. But then if you're floating above and you could also pick up these pre-eruptive rumblings from the air, that kind of adds information to this volcano eruption warning kind of system. So that would really be the intent, is to understand three-dimensionally what the volcanic eruptive sound or pre-eruptive sound looks like, and help warn major eruptions afterwards.
Very cool.
Yeah.
So cool to
It is.
hear.
It's a very fun project to be a part of, and yeah, it has both planetary and Earth-based applications, and all of this that I just said about like eruption monitoring on Earth is same thing can apply to Venus. On Earth, it's more of a public safety kind of also a science question, but like also a major public safety concern. But on Venus, it's like, oh, there's all this circumstantial evidence for Venus being currently volcanically active, but no one's ever been able to make a direct measurement. So it would be really cool to go there and be the first sort of instrument to pick up an ongoing eruption on Venus and and confirm it. So it is a really interesting piece of work like that we're so very proud of at this point.
And how did you guys come up with, how did the balloon come about? I mean, was it a tool you guys used for other things and just tried it on this aspect of the program? How did that come about?
Well, this is actually it's been a long time in the making. So there were a few French researchers in way back in 2004, 2005 who postulated that, hey, Venus's atmosphere is so thick that we could potentially pick up these acoustic waves from seismic activity from balloons. And then there was this workshop held at Caltech in 2015, 2014, 2015. This was even before I joined JPL, so it predates me. And where this was kind of adopted, like this framework where you could either measure ground motion from the surface, or you could measure it from a balloon, or you could measure it from a satellite, and all these three ways are complementary. That's where this idea of using balloons to measure seismic activity was really solidified. So, but since I joined this project in 2017, we've really been striving to make experimental demonstrations of this. So that's kind of when we started. And initially, we were using these balloons that we tied to the ground, so tethered balloons, and we didn't go for natural seismic activity. We used these things called seismic hammers, which produce artificial seismic activity to measure these sounds. And so we've gone through a steady progression of theoretically studying it, and then mission wise like accepting the concept, and then like now we're in the experimental demonstration part. So even in that, we've gone through a whole sequence of artificial seismic activity, and then like now there's like an uncontrolled experiment with like natural seismic activity, which I think is the most faithful demonstration of this technology. Right. So we've had this idea of flying a balloon over a natural earthquake for a while. We're actually going to go to Oklahoma this summer and the next summer for an entire summer-long campaign of flying balloons in Oklahoma, because there are a lot of earthquakes there. But when the Ridgecrest quakes happened, we were sort of in preparation for this campaign, and one of our program managers at JPL had this brainwave that there is this earthquake, there's a lot of aftershocks happening, and there won't potentially be another opportunity like that where there's like such a sure shot occurrence of events, because it was like hundreds of earthquakes every single day for weeks on end. And so we put together this very rapid response campaign where we didn't have these balloons. We had to make these balloons from scratch. We made these balloons, we prepared our instruments because they hadn't flown in this environment. And then we launched, within 2 weeks of the main Ridgecrest, July 4th and July 6th earthquakes, so about July 22nd was when we flew the first 2 balloons. And this presented a unique opportunity precisely because of the number of aftershocks and the strength and how compact it was. Like the target area to fly over was so well defined because all the quakes were happening along this Owens Valley area. So we knew exactly where we had to go, and we were fairly certain that something would happen while we were flying. Detecting the signal, of course, took a lot of work. There was a lot of analysis work that followed. So, which is why the papers coming out 2 years after the actual flight happened, because all of this analysis work went into it. But yeah, I mean, it was unprecedented as an opportunity. The Ridgecrest quakes.
Awesome. Excited.
Yeah, I mean, in very simple terms, it's like, I mean, the idea is so elegantly simple. Is, when you basically, if you thump your table, the air above the table will shake just the same way your table is thumping. Imagine the table was the Earth's surface, and an earthquake thumps to the table, and the air above it shakes, and we pick up those air shakes instead of the ground shakes. And so it's really just elegant and simple as an idea, and it allows for something that's not been done on Venus, and like, is currently not possible to do on Venus with high temperature technology. So it allows for a study to happen with current day technology versus like waiting for many years to develop something for the surface. So I especially like it because of that. It's just like, as an idea, it's very elegant in its simplicity. I mean, it's obviously harder than the principle of it, but just the principle is so nice and neat, that I really like that.
And lastly, so you were talking about Oklahoma. Just again, now the paper's out. You guys have done the analysis. What's the next step?
So the next step is, there's many ingredients that go into it, right? Like, so doing this on Earth, uh, one of the advantages we had was we have a lot of knowledge about what's going on the surface, because there are so many seismometers. And so, like, in terms of identifying the signal, that made our life easier because, we knew where to search. But going to Venus, we have no idea. We're like basically flying blind. And so our next steps are essentially collecting a lot of earthquake data. So like what we're trying to see is, when we collect a bunch of earthquakes this way from a balloon, are there patterns to earthquake signals? Because, you can imagine flying on a balloon with a pressure sensor, you see a lot of wiggles and a lot of noise, myriad things. And somehow you have to figure out, oh, this is a quake, and this is what the quake is telling me about what's going on the surface. And this kind of process involves having a lot of data, because then you can start spotting patterns in the data. And so for Oklahoma, that's really the aim is, we collect a bunch of these signals from a lot of quakes happening. So we do like a lot of overflights of the seismic area. And then we take these results and we project them to Venus. So we have models for the atmosphere of Venus, and then we have models for the subsurface of Venus. And so we take our tools for Earth and then we translate it to Venus and then make predictions for Venus. So that's basically where this is going next.